All right, we're here just one couple steps, more steps away from completely deriving the D5d character table. And we're trying to come up with the two last irreducible representations. I've actually erased the gamma symbols because soon we're going to have to erase those and put in the Mulliken symbols once we figured out what everything is. And so our idea here was that we have these two more one-dimensional um, relationships to figure out one-dimensional irreducible representations. We've tested all of our linear functions, quadratic functions, even some cubic functions to help us derive the first six irreducible representations. Why don't we try a rotation vector RZ? Remember what a rotation vector is it's described by basically a rotation around the principal, around the axis that you define, so around the z-axis. Okay, so what happens when we do identity on a rotation vector? Well, we just always get the same thing back, so that doesn't help us. That's going to get us a 1. What happens when we do a C5 on it, right? That's a 72-degree rotation, and that C5 is around the z-axis. So if we started something, if we draw it like this, and now we did 75-degree rotation, 72-degree rotation, excuse me, C5, 360 over 5, we're going to get something like that, right? The positions are going to change of the head and tail, but this vector is still rotating in the same direction. In this case, I chose counterclockwise. So RZ still goes to RZ. And so our value here is going to be a 1. And then if we look at C5-2, it's going to be a very similar situation. We just rotate a little bit more, right? Another 72 degrees. So still pointing in the same direction. An interesting one is a C2 prime, right? We define that as our x-axis. And now we're taking this vector basically and rotating it this way. Well, if we do that, that flips the position of the heads and tails. And so before we're going counterclockwise, now we're going before we're going counterclockwise, now we're going clockwise. So the negative, the direction has changed. And so that's the definition of being the negative of itself. So in other words, when we did a C2 prime, a particular C2, RZ went into negative of RZ. So our character there is going to be -1. Inversion is an interesting one. It ends up being a +1, and I'll show you why. Remember, inversion definition is x, y, z goes to negative x, negative y, negative z when we do an inversion operation. So what does this mean for a rotation vector? Well, if we start off with something like this, um, we think about this qualitatively as something at the top goes to bottom, something left goes to right, something front goes to back. Well, this is on the right. So let's see. So let's say the origin of the tail, the tail is at the top, right, and kind of in the middle. So that's going to go bottom middle, and then here it's bottom right. So that's the tail is gonna be top left. But then let's think about somewhere we need 3 points because 2 points just is a line. If we want to make a curve, we need 3 points. So let's think about the center of kind of in between the uh, uh, head and tail. That's on the left middle. So that's going to be right middle. So this is the center of the two. This is where the head went to, right? It went from bottom right to top left, and now this is the tail. So we end up getting something um, like this. And if we look at that, right, still in the same direction, counterclockwise, counterclockwise. So we get a 1. So inversion, a little hard to visualize, but you work through it like this with 3 parts of your vector, and you actually get it not changing. So RZ went to RZ. Um, next one is an S10, 3 times, as it turns out. It doesn't really matter too much, but that, remember, is equal to C310, a C10 3 times followed by sigma H 3 times. Of course, if you do sigma H, we've been over this a bunch in these derivations. 3 times, that's just equal to doing 1 time. But a C10 3 times, we already determined rotations in the across the z-axis don't do anything. So at this point, all we're doing is a flip, okay? So we have to think about this um, rotation vector sitting on top of this mirror plane looking at itself, right? And where is this actually rotation vector exists? You know, we just said it's wrapping around. I drew it above. If I drew it above, then well, fine. It would look at itself below, but it'd still be going the same direction. Or it could be in the mirror plane. It's still gonna not do anything. So that's a long way of saying this is a 1. S10 is going to be a 1 for the exact same reasons. Remember, an S10 is just a C10 followed by sigma H. So sigma H we just turned to nothing and the rotation to nothing. So overall, we've done nothing. Then an interesting one is the dihedral mirror planes. Well, the dihedral mirror planes contain the z-axis. So whichever one you choose, there are 5 of them. Whichever one you choose, right? These are 2 that I just kind of drew. They're all off axis because of the weird 72-degree angles that are involved here in the symmetry. But they're going to be cutting through. The top of this mirror plane is going to be cutting through here. And so if you're bisecting your vector, right, that's going to switch your head and tail. Your head's looking at your tail, tail's looking at your head in the mirror. And so that's going to change your direction. You can see that this was counterclockwise and now clockwise. So that's going to be a -1. And that is RZ. And that indeed is a new irreducible representation. As always, it's good to check that this is going to be orthogonal. It is, or with all the vectors, it is orthogonal with gamma 1. We can see that very quickly because there's 1s across the board for gamma 1. And we have 6 positive ones that sum up to 10, right? 1 plus 2 plus 2 plus 1 plus 2 plus 2. And then we have 2 negative ones that also sum up with 10. So those can cancel each other out, get the dot product equals 0. Just doing that math very quickly. More of these derivations you do, you'll get quick at them. And then the last irreducible representation, you're going to have to just look at it through orthogonality. There isn't a simple function that transforms like this. And I'll show you a trick of how I was able to find this one quite easily, very quickly. And the trick is that if I look at if I look at the again gamma 1, right? Thinking about gamma 1, and we want groups of 10 to be -1s, right? So you can see how we just did that I explained that for this one. This is gamma 1, by the way, right? Did that for gamma, what is this? Gamma 7. Now we're trying to figure out gamma 8. And so it worked here, right? Because we had we had 5, 6, 8, 10 -1s, and then 5, 9, 10 -1s. Well, another way of grouping this is just so we have 1s across the board in the beginning. That's going to get us 10. It's a grouping we haven't had before, and then -1s across the board. That's another grouping of 10. It's just a way of getting up to 10 with negatives and positives that gets you orthogonality being gamma 1. And if you check this with all the other ones, indeed, that is correct. So at this point, we have derived everything. The last one is just a little bit of puzzling out and, can take you a various amount of time to figure that out, make sure everything's orthogonal. But now we go and put in our Mulliken symbols, and we use an A or B if we have a dimensionality of 1. That's our Mulliken symbol rules. I have a video on that. And we use an A for symmetric with the principal rotation axis, which of course is C5. And if we're antisymmetric, that means if we have a -1, we use a B. Well, this is going to be an A because we're 1 and 1, A because we're 1 and 1, A because we're 1 and 1, and A. Okay? No B's in this one. And then we use a Mulliken symbol of E if under the identity class we have a 2. So those are all going to be e's. And then we use ones or twos as subscripts um, if we are symmetric or anti-symmetric with the perpendicular C2s. If we have that in point group, we do have perpendicular C's here. So we're one for symmetric, and then anti-symmetric, you put two. So I have a -1 here, a -1 here, so I put twos. Um, it gets a little interesting with the E's. We're going to skip that for now because actually uh, there's no symmetry here, right? It's zero. You can't really say anti-symmetric or symmetric. So it becomes actually totally arbitrary at this point for the E's, but let's skip that for now because that's just weird. Yeah, there's some ambiguity in the Mulliken system naming system. And so you just got to make sure you're talking about the same thing when you're doing a homework problem or whatever it is. But we do use the U's and G's for inversion. Ungerata for U is when it's anti-symmetric, and Gerata G when it's symmetric with inversion. So we got a G there, +1, and a G there, +1, and then a U with a -1 with inversion and a U. So those A's are now all differentiated. So those Mulliken symbols are done. For -2 here, that's a U, +2 there, that's a G, +2 there, it's a G, and -U there, -2 there, it's a U. And then it turns out that uh, the convention for these, this D5d is that the 2 cosine 2 pi over 5, 1 gets the value of 1. Okay. And oops, sorry, 2 cosine 2 pi over 5, 1. And the 2 cosine 4 pi over 5 gets the value of 2. But there's no way to know that a priori. And again, the normal Mulliken symbol rules here don't really apply because all these values are 0. But anyway, at the end of the day, those are just labels to help people communicate with one another. And, people are pulling up character tables. Hopefully now you understand where this character table comes from. It's a long one. And here's, what you might look up online. We got all the features in here. The only thing we didn't show is some of these cubic functions that we didn't need to use to draw the irreducible representations, or this Rx minus Rx and Ry that they transform also as E1G, as does XZ and YZ, although we showed that. So hopefully you enjoyed this derivation, and we'll see you next time.